In this video, we're going to begin using the Hardy-Weinberg theorem to solve some population genetics problems. So let's take a closer look at the theorem and just remind ourselves, first of all, what the different parts of it stand for. So the P and the Q in the equation stand for the alleles that we have. So if we write those out, the P will represent one of the alleles, Q will represent the other one. Depending on your problem that you're solving, you might designate those alleles in different ways. In this equation, as you see it written, the P is representing a capital A and the Q is representing a lowercase a. But again, these would vary depending on what allele names you have given to your genetics problem. Now, if we actually just talk about P, P would be the frequency of the A allele, and Q would be the frequency of the little a allele. When we put it together as we see in this equation, P squared is the frequency of the big A genotype. Q squared, on the other side, is going to be the frequency of the little a genotype. And then here in the middle, the 2PQ, that would represent the frequency of the heterozygous genotype. Notice that if we put all of them together, they should sum up to 1. So we could add these together, they would equal 1 as we see here. And another thing we're not actually seeing written on this slide is that the two alleles, if it is just two alleles in the population, those frequencies should also sum up to 1. So let's keep all of this in mind as we start to go through and actually work our genetics problems. So in this first one, you have sampled a population in which you know that the percentage of homozygous recessive genotype is 36%. So let's write our equation out here. We had P squared plus 2PQ plus Q squared, and that's going to equal 1. And so we do have a part of this equation that represents the little a genotype, and that's this part right here, the Q squared. So little a, we're told is 36%. So that really would be what the Q squared is representing. So that's the first question here. What is the frequency of the little a genotype? Well, that part's easy. It's 36%, or you could also write 0.36, same difference there. And then the second one, we want to use this information to figure out the frequency of the little a allele itself. Well, if Q squared equals 0.36, and we want to know what Q is, then all we have to do is take the square root of both sides here. So if you do that, go ahead and plug that into your calculator if you need to. And when you do that, the square root of 0.36 is going to be 0.6. So that would be the answer for this one here, 0.6. That's the frequency of just the little a allele. If we want to know the frequency of the big A allele, keep in mind the other part to the Hardy-Weinberg theorem, which is that P plus Q equals 1. Well, we just solved for Q. That was 0.6. And so we know P plus 0.6 is going to equal 1. So all we have to do in this case is solve for P. So P is going to be equal then to 0.4. So we can write that here. And then the last question is, what are the frequencies of the other two genotypes that we're looking for? So we want to know the frequency of big A, and we also want to know the frequency of the heterozygous ones. Those are the other two parts of the equation here. So P squared would be the frequency of big A. Well, since we know what P squared is, that would be a very simple one to do. So for that, to figure out this one, we're going to take P squared, which keep in mind that P is going to be 0.4. So we're going to take 0.4 squared. And that's going to be equal then to 0.16. So the frequency of big A is going to be 0.16. And then if we're talking about the heterozygous ones, that would be the 2PQ. So for the heterozygous ones, we're going to take 2 times the frequency for P, which is going to be the 0.4, times the frequency for Q, which is 0.6, and then we're going to just multiply that out. So go ahead and plug that into your calculator right now. Okay, so that should come out to 0.48. Hopefully that's what everyone got when you plugged it in. And so that's all of the questions solved on this slide. Now to put just a few things together, we said that P plus Q are going to equal 1. If we also add together all the different genotypes, they should equal 1. So let's go ahead and do that just to double check. The frequency of big A was 0.16. The frequency of the heterozygous ones we saw to be 0.48. And then the frequency of the little a was 0.36. So when you add all of those together, it is going to come out to 1. So that's just one way to double check our math, make sure we did everything correctly. Now I just want to jump in here for a moment and mention that as we go through and solve these genetics problems, certainly feel free to pause the video as we go through them, try to solve them on your own, and then restart the video and see if you're coming up with the correct answers. Let's take a look at this next one. Within a population of butterflies, the color brown, which is represented by the capital B, is dominant over the color white. Okay, so let's stop there for a second and we can take our P and Q and just assign them to the alleles. So we're going to take the P and use that to represent the capital B, and we're going to take the Q and use that to represent the lowercase b. Now we're told that 40% of the butterflies are white. Okay, keep in mind, again, if we're talking about the Hardy-Weinberg, P squared represents the frequency of the dominant ones, which would be capital B, capital B. Q squared would represent the frequency of little b, and then 2PQ is going to represent the frequency of the heterozygous ones. So keeping that in mind, first of all, we're asked, what is the percentage of butterflies in the population that are heterozygous? Okay, well that would be, we just said that to figure out heterozygous, that would be 2PQ. Okay, we have to know what P is and we have to know what Q is if we're going to solve that part. So we need to be able to take the 40% and figure out P and Q. Okay, so 40% is the frequency of the ones that are white. So 40% is basically right here. So Q squared is equal to 0.4. If we want to figure out what Q is, then we take the square root of both sides. Okay, so go ahead and take the square root of both sides and figure out what we have for Q. Okay, so if you plug that into your calculator, hopefully you came up with 0.63 for Q. Okay, so we're just going to round that to 2 decimal places. So we know what Q is. Keep in mind that P plus Q has to equal 1, and we just solved for Q. That was 0.63. So knowing that, it should make it relatively simple to solve for our P. So if we do solve for P, go ahead and punch that into your calculator. P is going to be equal to 0.37. Okay, so we're just taking 1 minus 0.63 to come up with that number. So here we know what Q is. Right here we know what P is. And all we have to do is plug them in to get what 2PQ equals. So we're going to take, to figure out the population, the percentage that's heterozygous, we're going to take 2. We're going to multiply that by P, which is 0.37. And then we're going to multiply that by Q, which is 0.63. Go ahead and figure out what that multiplies out to be. All right, so I came up with 0.4, we'll round that to 0.47. That's the frequency of the heterozygous ones. So that's going to be big B, little b that we just solved. The next step is to figure out the frequency of the homozygous dominant individuals. Well, the homozygous dominant would be our capital B, capital B. And keep in mind that capital B is going to be represented by P squared. Since we already know what P squared is here in the middle, this is a simple one to work out because all we have to do is take 0.37, square it. Go ahead and figure out what that is. And now we're just going to round that. So we're going to come up with 0.14. That will be our frequency of capital B, capital B. Now at this point, Just to double check everything, let's go ahead and add up the different genotype frequencies to see if they do sum up to 1. So we know that for capital B, we have 0.14. For our heterozygous ones, we have 0.47. And then for our little b, we have 0.4. That was information that was given to us. So all of those added together it's going to come out to 1.01. Okay, so that's very close to 1. It's probably just a rounding difference in this case. So they do add up to 100%, which is what we're looking for in this case. Next question. Cystic fibrosis is a recessive condition that affects about 1 in 2,500 babies in the Caucasian population of the United States. Okay, so cystic fibrosis is recessive. So that means that it's going to be the recessive allele that carries this cystic fibrosis, and you would have to have the recessive genotype to actually have it. So the first question is, what is the frequency of the recessive allele in the population? Well, let's take a look at the information that we have just a little bit closer. If somebody has cystic fibrosis, they have the recessive genotype. So they would be little a. Well, we're told here that this is going to happen in 1 in 2,500 individuals in the Caucasian population of the United States. So that right there really is our genotype frequency. So to figure out what little a would be, which is the same as asking what q squared is, because remember that q squared represents little a, we basically just need to divide 1 by 2,500. So I'm going to do that. Okay, and what I'm coming up with is this right here. Okay, 0.0004. So that's going to give us q squared. If we want to figure out what q is, which is what we're asked in the first question, if that's q squared, then to figure out q, we simply need to take the square root of both sides. So go ahead and do that. And so for q squared, or q, you're going to get 0.02. Okay, so that's the frequency for q squared. That's the answer to the first question here. The next question is, what is the frequency of the dominant allele in the population? Well, keep in mind that p plus q equals 1. So if p plus q equals 1, all we have to do is plug in q here. So we know what q is, and we can solve for p. So p is going to equal 0.98. The last question asks, what is the percentage of heterozygous individuals in the population? These are individuals that we would call carriers because they're going to actually carry that cystic fibrosis gene, but we're not going to actually know that they carry it. Well, the heterozygous ones are 2pq. So if we plug in what we know, we have 2 times p, which is 0.98, times 0.02. Multiply that out. And we've got essentially 0.04. Okay, so if we look at that as a percentage, that's about 4% of the population, Caucasian population in the US, is going to be a carrier for cystic fibrosis. To look at yet another one, the ability to roll the tongue is controlled by a single gene with 2 alleles. The allele for being able to roll is dominant over the allele for not being able to roll. In a given population of 10,000 individuals, there are 7,399 tongue rollers and 2,601 non-rollers. Okay, so we're going to assume that the population is at Hardy-Weinberg equilibrium, and we want to know how many heterozygous tongue rollers are there in the population. Okay, so we can't just look at someone and tell that they are a tongue roller, because there's both the big R and the heterozygous ones that look exactly the same, or both display this tongue rolling. So we have to take this information and we have to use it to figure out the heterozygous percentage. The easiest way to go about this is to look at these guys, okay, the non-rollers, because that's the little r. And remember that little r is basically Q squared. So our total population is 10,000. So Q squared is equal to 2601 over 10,000. That would give us the frequency of that particular genotype. So go ahead and divide that out. Okay, so the percentage when you do that is going to be, or the decimal is going to be 0.26. So if Q squared is 0.26, so I'm just going to write that here, that little r is going to be 0.26. That means that, so that's equal to Q squared. If we want to know what Q is, we take the square root of both sides. Okay, so take the square root of 0.26, and that will give you the frequency of the R allele, or Q. So that's going to be equal then for Q to basically 0.51. If we want to figure out what P is, remember that P plus Q equals 1. So we know what Q is, 0.51. So if we solve for P, P is going to be equal to 0.49. Okay, so very similar allele frequencies for these two. And if we answer our question here and we want to know how many heterozygous individuals we have, well, heterozygous is 2PQ. So we're going to take 2 times the frequency for P, which is 0.49, times the frequency for Q, which is going to be 0.51, and see what that comes out to be. Okay, so our frequency of heterozygous individuals is 0.499, so we'll say 0.5. Okay, so 0.5 will be the answer to this particular question.